In this video, we will learn about compliance of lungs. First, we will understand what compliance means. Then we will see what determines compliance. And finally, we will see compliance diagram of the lung. Let's get started. As usual, we have schematic diagram of lung. This is lung parenchyma, this is alveoli, and this is pleura. Here, transpulmonary pressure is pressure across alveolar wall. It's pressure difference between alveolar pressure and pleural pressure. As this pressure increases, the lungs expand. Or in other words, with increasing transpulmonary pressure, lung volume increases. Compliance is extent to which lungs expand with unit increase in transpulmonary pressure. That's change in lung volume with unit change in transpulmonary pressure. It's basically measure of extensibility of lungs. Higher compliance means it's easy to expand lungs, and lower compliance means it's harder to expand lungs. Now let's see what determines lung compliance. It is determined mainly by two elastic forces. Elastic forces of lung tissues and elastic force caused by surface tension of fluid that lines the airways. Lungs have elastin and collagen fibers. In deflated state of lungs, these fibers are kinked. As the lungs expand, these fibers get stretched and exert elastic force on the lungs. Now surface tension. Alveolar wall is lined with fluid. This fluid comes in contact with air in the airway. So we have air-water interface here. Surface tension at this interface tends to collapse the airway. In doing so, it exerts elastic force on the lungs. Thus, these two forces determine lung compliance. The higher these elastic forces, the harder it is to expand the lungs, or lesser the compliance. Now let's see compliance diagram of lungs. First we will see extent to which lungs expand with increasing transpulmonary pressure. And then we will see same changes in graph. Okay, so this is collapsed lung. See, the elastic fibers are contracted and kinked, and airways are completely collapsed. Increase in transpulmonary pressure in initial phase does not expand the lungs much. The reason here is very high surface tension of these completely closed airways. When lungs are collapsed, surfactants are minimal. So surface tension is high and it takes extra efforts to overcome it. With further increase in pressure, the surface tension is overcame and airway starts opening. Now the increasing pressure expands lungs more and more. Towards total lung capacity, muscles approach the stretch limits and there is no further expansion. Then as the transpulmonary pressure decreases, lungs collapse. But by the time the lungs expand, surfactants come on the surface and decrease the surface tension. Because of this decreased surface tension, the trend of collapse is different from that of expansion. Let's see it. Initially, fall in transpulmonary pressure causes smaller deflation of lungs. The reason, as I said, is surfactants. Due to decreased surface tension, it's easy to keep lungs expanded even at lower transpulmonary pressure. With further decrease in transpulmonary pressure, lungs eventually collapse. So this is how lungs inflate and deflate with changing transpulmonary pressure. Now let's see same changes in form of graph. In this graph, x-axis shows transpulmonary pressure and y-axis shows lung volume. We start from this point where lungs are completely collapsed. Initially, as we rise the transpulmonary pressure, there is small change in lung volume. This is because of very high surface tension due to deficit of surfactants at air-water interface. With further increase in pressure, the surface tension is overcame and airway starts opening. So further increase in pressure results in almost a linear expansion of lungs. Then as we approach the total lung capacity, the expansion rate again decreases. By this time, surfactants appear on the air-water interface. So surface tension is decreased. Because of this, deflation takes different route. Fall in pressure initially causes smaller decrease in lung volume. This is because surfactants have decreased surface tension. so it's easier to hold airways open even with decreasing transpulmonary pressure. With further decreasing pressure, however, lungs collapse and we reach the starting point. See how both the curves are different. The curve that is recorded during inspiration is called inspiratory compliance curve, and that recorded during expiration is called expiratory compliance curve. And the entire diagram is called compliance diagram of the lung. The difference in inspiratory and expiratory curve is called hysteresis. The reason for this difference, as we have already seen, is surfactants. In collapsed lungs, less surfactants are there on the air-water interface, and surface tension is high. So at this point, it takes extra pressure to pop open the closed airways initially. However, in inflated lungs, surfactants have came on the interface and have decreased the surface tension. So now it's comparatively easy to keep the airways open. So that's the reason behind hysteresis. Conventionally, this deflation curve is used to measure compliance of lungs. Finding the slope of the curve gives the value of compliance. Note that the compliance is different at different lung volumes. At lower range, the compliance is high. Means there is rapid increase in lung volume with increasing transpulmonary pressure. At higher ranges, the compliance is less. Means there is relatively small change in lung volume with increasing transpulmonary pressure. Thus, the compliance is higher at lower lung volumes as compared to higher volumes. Now during normal breathing, parameters move back and forth between these 2 points. This is point after restful expiration. The transpulmonary pressure is about 5 cm of water and lung volume is at functional residual capacity. After inspiration, transpulmonary pressure increases to about 7.5 cm of water and lung volume increases by tidal volume. After expiration, it comes back to the starting point. During normal breathing, hysteresis is much less. That's all about compliance of lungs. Let's summarize everything. Compliance is extent to which lungs expand with unit increase in transpulmonary pressure. It's change in lung volume divided by change in transpulmonary pressure. It is determined by elastic forces of lung tissues and surface tension. Now compliance diagram. When inflating lungs, initially increasing transpulmonary pressure produces small increase in lung volume. This is due to high surface tension. With further increase in transpulmonary pressure, surface tension is overcame, airways open, and lungs expand almost linearly with increasing pressure. Then rate of expansion decreases towards the total lung capacity. Due to decreased surface tension, the deflation of the curve takes different route. The reason is presence of surfactants make it easy to keep open the already open airways than to open the closed airways which have less surfactants. The difference in inspiratory and expiratory curve is called hysteresis. Conventionally, deflation curve or expiration curve is used to measure the compliance. The compliance varies with lung volume, and in general, it's higher at lower lung volumes and lesser at higher lung volumes. During normal breathing, the parameters move between these 2 points located near deflation curve, and it exhibits